Hand someone a shuffled deck of cards. Tell them, cut it wherever you want, look at the card, and start counting through the deck from there. Face value tells you how many cards to skip. Jack, queen, king all count as 5. Ace is 1. Keep going, card after card, chaining from count to count. They do this silently. You're not watching. You couldn't possibly know their starting point or their path through the deck. And yet, 9 times out of 10, you name their final card. This isn't a shuffle trick. It isn't a stacked deck. It's a magic trick powered entirely by a piece of mathematics called the Kruskal Count. And it works because of something strange and true about long chains of random choices. Independent paths through the same sequence tend to collide. Let's define the trick properly, because the math only makes sense once the rules are clear. Take a shuffled deck. The spectator picks any starting point in the first several cards. Their choice, totally free. They look at that card's value. Face cards and tens count as 5. Everything else counts as its number. Ace as 1. That number tells them how far to jump forward. Land on a new card, read its value, jump again. Repeat this all the way through the deck. Eventually, they'll run out of room to make a full jump. That last card they land on is their Kruskal card. Here's the part that sounds impossible. 2 people starting at different random positions will, with very high probability, land on the exact same Kruskal card by the end of the deck. Not because they're doing anything the same, because of the deck itself. Let's actually run it so this isn't abstract. Say the top of the deck, in order, has values. Value 4, jump 4, lands on position 5. Value 6, jump 6, position 11. Value 3, jump 3 to position 14. Path B starts at position 3. Value 9, counts as 5, jump 5, lands on position 8. Value 8, jump 8, position 16. Different starting points, different early trajectory. But notice, both paths are now bouncing around the same fixed sequence of upcoming cards. Every jump either lands exactly on the other path's future position or it doesn't. And if it doesn't, the next jump gets another independent-ish chance. Run this 40 or 50 times in your head across a 52-card deck, and paths that seem to be doing their own thing keep almost tripping over each other. Eventually, usually, one lands exactly where the other already stepped or is about to. That's the moment of merge. From there, both paths are reading the same cards in the same order, making the same jumps forever. The intuition starts with something called a coupling argument, and it's easier to see with a simplified example first. Imagine 2 people walking through the same sequence of cards, taking different size steps that depend on the cards they land on. As long as the values are small compared to the deck, 1 through 5 in this case, every card in the deck acts as a potential landing spot for a huge number of different paths through the earlier cards. Think about it from the deck's point of view, not the spectators. Any card in the middle of the deck can be reached by paths starting from many different earlier positions. Some starting points land exactly on it, others jump right past it. But because jump sizes are small, 1 to 5, the coverage of possible landing spots is dense. Once 2 people's paths land on the same card even once, they're synchronized for the rest of the deck. Same card, same value, same next jump, forever after. This is the crux of it. You don't need the paths to start together. You only need them to intersect once. And in a 52-card deck with jump sizes of 1 to 5, the probability that 2 independent random-ish paths fail to intersect at all before the deck runs out is small, usually under 10%. It's the same logic structurally as the birthday paradox, where a room of just 23 people has better than even odds of a shared birthday because you're not checking one pair, you're checking all pairs at once. Here, you're not checking whether the paths match at one particular card. You're asking whether they ever cross over dozens of chances, and dozens of chances at collision is a lot. Let's get slightly more precise then. It usually works, because the actual number is more interesting than the vague version. At any given card, roughly how likely is it that this specific card is a landing spot for some path, any path, starting somewhere nearby? With jump sizes from 1 to 5, roughly 1 in 3 cards ends up being a landing spot when you average over all the ways to arrive there. That's not a coincidence. It falls out of the average jump size. Average a jump of roughly 1 through 5, weighted toward the middle values in a real deck, and you get something close to 3. So roughly 1 in 3 cards gets hit. Now stretch that across the deck. If a given card has something like a 1 in 3 chance of being a shared landing spot, and there are dozens of cards left after each starting position, the question becomes, what's the probability that none of those chances hit all the way through the deck? This is exactly the birthday paradox logic, just dressed differently. In the birthday paradox, you're not asking, will person A share person B's specific birthday? That's unlikely. About 1 in 365. You're asking, across many pairs of people, does any pair match? And with enough pairs, unlikely events start stacking up into a near certainty. Here you're not asking, will path A land exactly on path B's very next card? You're asking whether, across dozens of opportunities strung end to end, they ever converge, compound a 1 in 3-ish chance of intersection across enough attempts, and the chance of complete avoidance shrinks fast, down into single-digit percentages by the time you reach the end of a 52-card deck. That's where the roughly 90% plus success rate performers rely on actually comes from. So the deck does the heavy lifting, but performers exploit 2 more things to push the odds even higher than the pure math trick. First, the starting position isn't as free as it looks. People instructed to pick a number between 1 and 10 don't pick uniformly. They avoid 1 and 10 as too obvious and cluster on 3, 4, 5, 6, 7. A skilled performer nudges the effective range of starting points to be smaller than it appears, which increases the chance of collision with the performer's own tracked path, because narrower starting spread means fewer distinct trajectories to reconcile. Second, the performer runs their own count in parallel, silently, from a starting point they chose. They're not reading minds. They're doing the exact same walk, betting that probability will bring the 2 paths together, and when it does, they simply know the spectator's final card because it's the same as theirs. The trick is a real magician performing a real verifiable statistical bet and losing that bet quietly, roughly 1 time in 10, which is why good performers frame the reveal. So a near miss, you're thinking of a card near here, still looks impressive. The trick is named after Martin Kruskal, a mathematical physicist, the same person known for co-discovering solitons, the self-reinforcing solitary waves that show up in everything from water channels to fiber optics. He wasn't a magician. He stumbled onto this forced card behavior almost as a curiosity, a side effect of thinking about how deterministic-looking systems can still exhibit unpredictable, chaotic-seeming paths that nonetheless collapse into shared behavior. Magicians got hold of the idea later, most notably popularized by writer and mathematician Martin Gardner, who spent decades translating exactly this kind of real math disguised as impossible magic for a general audience. The trick's real name in magic circles is often the Kruskal principle, or simply a Kruskal force, and it's become a staple precisely because it needs no sleight of hand, no marked cards, no secret peek. The deck itself does the forcing. Because it's genuine probability and not a guaranteed mechanism, it's worth being honest about the failure mode, since that's part of what makes it real math, instead of a magic claim. Failures cluster around 2 situations. First, starting positions that are too close to the end of the deck, where there simply aren't enough remaining cards to generate the handful of chances to collide. that make the convergence likely. Fewer opportunities means the birthday paradox style stacking never gets going. Second, unusually long, low value runs, strings of aces and twos, which produced longer chains of small jumps, and small jumps landing in a tight cluster of cards can occasionally desynchronize two paths that would otherwise have merged because they keep landing one or two cards apart instead of exactly together. A performer manages this by starting their own silent count somewhere in the first third of the deck, giving both their path and the spectators the maximum number of remaining cards, and therefore the maximum number of chances for something in the middle of the deck to make the two of you land on the same card. Here's what makes the Kruskal count worth knowing beyond the party trick. It's a hands-on demonstration of convergence in Markov chains, systems where the future only depends on the present state, not the history that got you there. Once two paths land on the same card, their entire future is identical, regardless of how different their pasts were. That's the Markov property in its purest form. The past becomes irrelevant, the instant states align. It's the same underlying mathematics used in Google's PageRank algorithm, which models a random surfer clicking links. Different surfers, different histories, but their long-run behavior converges onto the same distribution of important pages. Weather models and genetic sequence analysis, where independent simulations run long enough, tend to forget their starting conditions. Shuffling theory itself, the reason 7 riffle shuffles is the accepted threshold for truly random, is a convergence argument of exactly this type. The card trick isn't a curiosity sitting outside of real mathematics. It's a low-stakes, fully visible instance of one of the most useful ideas in probability. That independent random processes sharing a common structure will, more often than not, forget their differences and merge. So next time somebody shows you a mind-reading card trick with no gimmicked deck, no forced card, no sleight of hand, you don't have to accept magic as the explanation. You can ask a better question. How many chances did the two paths get to collide, and how small were the jumps? Because that's not a magician's secret. That's a Markov chain wearing a tuxedo.